Okay, so hello guys, I'm very happy to see you here. I'm Wojciech and here's Marcin, and we are working on Node Lab. And I've got one question, if I could, on the beginning. How many of you are programming in Haskell? Great. And how many of you have ever developed some extension to GHC? Okay. We'll have some fun here today, I think. But, we've got here some interesting material about our compiler and how we have implemented it in Haskell. And okay, we start with talking with you what you are doing.
So first, the fluffy part. I mean, we have flipped a coin. Who is doing the fluffy thing about what we are doing and so on, and who's going to the technical details, and Wojciech is going into the technical details. So I'm just here to show you what we are doing. And one sad fact at the beginning of this talk is that I know this is a Haskell meetup, but we are going to talk about things being easy. So yeah, this is pretty much our mission. We want to make functional programming and programming in general easy. Not simple, because Haskell definitely is simple, but easy. And for that, I will start with what's wrong with programming, in our opinion, right now. So we have basically identified. Okay, now our keys are working. Okay.
Oh, we probably lost focus.
Oh,
and this thing
no,
is
it's okay.
Okay. So first, there's a huge communication gap, and your job basically is to fill that communication gap. I mean, the software developer is basically a person that is his job is basically to translate requirements, to translate human ideas and human requirements into computer language. So this is what we do, and the problem is that there is still more and more tasks. Can we undo that thing?
I think we can still actually see the screen, but we can see it as well.
Okay. The problem is that we've got some animations here, and they will not be.
We can turn it off.
Or
Okay. Just let us know if something goes wrong.
okay, I will turn the hand control.
No, don't do this. Okay. Just keep quiet. So yeah. So this is what we do. We are trying to fill this communication gap, and basically more and more tasks in the world require programming. If you think about it, even marketing departments in big corporations right now need programming, because they need to process data from all those clicks on your e-commerce website. And so even the guys in marketing are doing programming, or they actually need programmers. And we claim that some of that programming they can do themselves. And you can think of this as the thing that Excel done with data analysis 15 or 20 years ago. Microsoft Excel brought some mathematical analysis to pretty much everyone. I mean, today everyone knows how to do basic mathematical analysis of data using Microsoft Excel. And we believe that this is also possible with programming today. The second problem is that we don't have collaboration in programming. We don't cheat ourselves. And you probably have heard in your companies where you work a million times that programming is a team sport, that we need collaboration and so on and so on. But still, we have two ways of collaborating. Actually, only one way of collaborating, which is pair programming, which is two people sitting at one desk using one keyboard, which is completely obsolete. And we have version control systems, which is not really collaboration. You don't have a way to fiddle with your code with your peer over the network. This is pretty much impossible right now. Then we've got the inherent complexity of software, and this is actually from a research paper that says that there is about 100,000 lines of code that an average good developer can retain in their mind. And this is probably about Java code, so you can like divide it by 10 for Haskell. So this is how much the small red square that is probably not visible from the back rows. This is how much you can retain in your mind using textual representation, a mental model. And this huge gray block out there represents software from a modern car. I think it's BMW or something like that. So this mismatch is huge. And this obviously comes from some inherent complexity in software that we cannot mitigate because software is complex. But this also comes from the fact that we are still using tools and representations that are not created for today's problems, that are created some 50 years ago and hasn't changed since. I mean, we have better languages, but we still do use text editors that were created like in the 70s or 80s, and nothing has changed in that area. Then we have the errors, and this is not the slide for you. I mean, you are using Haskell probably, so you already have all the static typing goodies, but I can see like, I don't know, 50 of you here, and the whole industry out there is doing crazy things in Ruby on Rails and JavaScript. And they are doing mission-critical things in Ruby on Rails and JavaScript. Yes?
Actually, like forgetting to convert would not be prevented by static typing, but I'm just...
We have the dimensions.
But that depends on how are you doing that. I mean, this is a scale where you can put yourself. You can basically new type for your measurements, for example, if you are crazy enough to do that. Or you have a type system that is not that is expressive enough to do that without so much pain. I mean, in Haskell that would be painful. If your type system is more automatic, that can be much better. And then my favorite part. So, parallel computing is the future. And we have a quote from Bartosz, who is here. And we really didn't know that he's going to be here, but yeah, you've got an expert in the audience. So parallelism is hard, and we need it. We seriously need it. And for most use cases, this can also be done automatically. Especially in the early days of the system where we don't need really, really high performance and so on. This can all be done very easily. So that's why we have created NodeLab and Luna, and we claim that they solve them all. This is marketing, okay? But yeah, we have the silver bullet for all the problems. And this is how it looks. So basically we have Luna. Luna is our programming language with double representations. So this is both visual and textual. It's purely functional. We will show you an animation in a second. And then we've got NodeLab. NodeLab is the whole like IDE or text editor, like text visual editor for the language. So yeah, here comes an animation. We like to call NodeLab a developer's computative whiteboard. Because when you start to design a system, you usually start there. You start at the whiteboard, and then you go to your code and you forget about the whiteboard. And this is where things get messy and everything just blows out. So as you can see, we've got nodes that are in one-to-one correspondence with lines of code, and the representations are isomorphic. So whenever you change the graph, the code is changed, and whenever you change the code, the graph is changed. So you can basically switch between the two representations at any time and decide for yourself which is better at the current situation. Because, for example, if you are doing some low-level stuff or just implementing some algorithm you probably can do on top of your fingers, you are probably going to use textual representation. It's just easier for us right now. Then if you are going to fiddle with the system, to actually see what's happening, visual is the way to go. So yeah, so this is what we have created, or actually what we are creating right now, and what we believe is the future of programming, at least some part of programming. So yeah, some of our most awesome features. We've got automatic parallelism because we have static typing below with monadic side effects and so on. So we basically know what functions are doing side effects, which are not, so we can automatically parallelize some things. Of course, it's not as good as you can do this manually still, but it's good enough for most use cases. Then we've got collaboration that looks like in Google Docs, which is impossible with textual code actually, because when you are changing something in the textual code, you never know if you are breaking something somewhere later in the flow. With visual representation, if you fiddle with some node, you can see what is affected by the change, and you can do this with your peer and actually see who is editing what. There was this is in here. So the posts node is edited by some Mark, and the select node is edited by some John. You can, I don't know, if you have some parameters there, you can just fiddle with them to interactively visualize what's happening in your system. And now there's some praise for the community and for the Haskell community in the first place, because our whole marketing strategy so far, okay, not whole, but most of it, was one message on Haskell IRC. Wojciech written there that, hey, we are just releasing Luna language, maybe you are interested in that. And we are in like an hour, we were the first topic on Hacker News, and on Reddit, I think it was the developer to subreddit or something like that. And in the first 3 days, we got over 1,000 responses to our alpha sign-up form. So this is pretty awesome, and this is thanks to you guys, mostly. And yeah, this is some praise from the community, which basically confirmed that, you know, this is the silver bullet and we are fucking awesome. This is actually said like second quote in the right column. And now what I want to show you, two more things. One thing is that this is actually something we are working on right now. So we know this is kind of crazy to bring a whole new language into the ecosystem, right? I mean, there's a whole lot of languages, and building community is a huge task. But because we are using Haskell like for everything, I mean we run on Haskell. Even our front end, which is WebGL, uses GHC.js. So Haskell bottom up. And so we've got Haskell, like foreign calls to Haskell out of the box. I mean, Haskell is just there. And we are also working on supporting Python and JavaScript and C++. And one more cool example that will show you what can be actually done in like some data-heavy industry, which is, in this case, it's IoT. So basically, imagine you are trying to design an intelligent building. A building that tilts its windows based on the temperature inside and outside the building. So, okay, there. So you just get a map of your home. You can get windows and sensors from there. For each window down, this is some cool magic. Just ping me later about this, and I will explain you how exactly this each is streaming each window from the building to the next parts of the computation. And big hint is the list monad, which is basically used in there. So then we for each window we select all nearby sensors indoors and outdoors. We get the value, we get the averages, and if the average inside is greater than 25 and the average outside is lower than the average inside, we just tilt the window, the particular window, because this is happening again for each window in the stream. So this is pretty much how that would work in a like production example. And now the promised part with nitty-gritty details of our compiler, given by Wojciech.
On the beginning, do you have any questions to Marcin about the whole concept? Yeah.
Okay, so how would you deal with more complex programs? Because those are obviously looking really nice, but you know, I have this kind of view of lab view in my brain of this, you know, huge graph of interconnected stuff. So how do you deal with those cases?
Okay, so that's a great question actually. So this is functions all the way down until you see the turtles. But this is functions. So if you double-click a node, for example, I don't know, maybe nearby looks like a complex computation, right? I mean, it needs to filter something and so on and so on. So if you double-click this, you get into the definition of this particular function. So the nodes in our case are hierarchical. So it's not like it's just a fixed set of them. This is a programming language. So basically, if you do def something or just use a lambda, you get a node. You can click into that node, edit it inside, and so on. So this is how we do it. Any more questions?
Can you like zoom out maybe and then like see this as a one node?
Exactly. Yeah. So you can for example change the definition of the nearby function, and then see what happens on the higher level and so on.
Moreover, you can, for example, select all the nodes without home and collapse them into one node and create a function that you can connect to any home in any building later. So yeah, you can define and collapse functions this way.
So what do the colors mean? And do you have different types?
These are types, yeah, exactly. So, of course, there are not as many colors in the world as there are types, but that would be crazy. But yeah, we are trying to visualize the possible types with colors.
If you want to ask how type checker of our language works, it is perfect place to ask it because Marcin was working on it recently. So
yeah, I'm like the guy behind the algorithms of the type checking. It's pretty awesome and pretty scary. So yeah, let's talk about it later probably. Yep.
Do you have support for automated testing in your language?
And not just yet. But yeah, this is something we need to work on.
Why don't you not extend a subset of Haskell?
That's because we want
not too much. Sorry.
Okay. So there's one thing about that. So we believe Haskell is pretty awesome, but for a person that is familiar with Python or R, it's definitely too complex. I mean, just explaining the concept of monads and do notations and why do you have, like, if you are not a programmer, grasping why do you sometimes need to use the right to left arrow and sometimes the equality sign, it's definitely too complex for them. I mean, they don't really want to know that. They don't have the incentives to learn programming at such a deep level. A data scientist usually just wants to do his data science stuff.
But monads are just a library, Haskell library. You don't need to use it.
They are pretty important if you, for example, want to do side effects, right? If you want to print something, you already need to learn something. So that's why we have a different approach to monads. We kind of do the plumbing under the hood, and everything in Luna looks like equality. So the whole monadic system. Do we have this? Where's the? Just a snippet of code. Okay, we have some code here, and as you can see, everything here. Even though this network.posts, this is probably a method that does some network code. This one here. Even though this probably does some method call, some network call, it looks pretty innocent in here. So the whole type system is kind of opt-in. If you want to have the safety, if you want to provide the safety, it's there. If you let us inference that this is a safe or unsafe, it's there. But it's up to you, like the level to which you want to.
Can I add something to that?
Of course.
So I would love to answer a bit deeper this question because we were in fact really thinking about it. If, for example, extending Haskell or making some DSL in it would be a good approach.
For effects, yeah. For other.
In fact, we've got also monads. Every line is also implemented as a library here, so you can involve monads in Luna. But answering the question, we were thinking about Haskell, and Haskell has some things that are really not easy to move into the visual representation. The first one is that it has type classes, and we can, instead of type classes, we have created here some object-like notation. It is not object-oriented language in the classical sense, but object and object notation with the full generality derived by Haskell is a really better way to work in the visual environment. And there are a lot of things like that. For example, the error handling. In Luna, all errors are traversing with the graph. So if, for example, something breaks, you're reading a file from the disk that is not there, you've got a broken value, something like automatic maybe or either. And these eithers are nested in our language. So for example, if you want to add there something or divide by 0, you can later catch
You have a library like that, don't you? Unreliable Haskell library. But perhaps it's a bit different.
Yeah, and in fact, having this as DSL, has a lot of limits. And I think that we can cover that in a moment when I will talk about the compiler. But after that, I would love to hear from you if I answered your question, or if we should dig that deeper. Thank you very much.
I think there was one more question like in the back, like, way before.
Is it possible to use Luna without NodeLab?
Yes, but that would be a bit painful. I mean, we are planning to open. No, we are just to clarify that. Don't get angry with it. First of all, we are planning to open source the whole Luna compiler. It's probably going to happen like in September. And then NodeLab is going to be free to use for commercial and non-commercial, like the NodeLab Community Edition. So Luna compiler is going to be open source, but you are not getting the whole awesomeness of NodeLab. So we are basically open sourcing just a binding, so you could probably create your own graph representation or just use the textual language. But this awesomeness here comes inherently from NodeLab, in my opinion at least. Yes?
I'm sorry I wasn't for the part of the presentation, but what will be the status of the NodeLab? It won't be open sourced?
Yeah, NodeLab itself, we haven't closed it yet, but it probably won't be open sourced.
Like money.
Yeah, we like money. I mean, after all, we are a startup, and right here it's called a pitch deck. So, NodeLab is not going to be open sourced. Most probably, it's going to be free to use.
So basically, NodeLab will be only the editor, but because what I am thinking about scientific use. So if, let's say, a scientist wants to analyze some signal using Luna and NodeLab, they create actual script like in IPython, and then they want to save it to actually add it as attachment to their publication. Are other scientists able to actually look at the code of the script without NodeLab? Are they able to just use the Luna compiler itself?
Yeah, that's what I said. You can just use textual Luna, and it's like fully blown programming language. It just lacks the awesomeness of visual representation. So I would imagine that a scientist would probably load some data into NodeLab, fiddle with it, find the answers, because like this is for data science. This is inherently awesome. You are just fiddling with the data in real time. You can just remove outliers and so on, just with a click, and then export your script, attach it to your paper, and it's there.
Additional, we provide something like NodeLab, hosted NodeLab. So if you got a script, you can just view it online, click just one link, and of course that will be also free of charge. So.
What do you guys understand by category-based programming? Because that's one of the slogans on your slide, and I was really intrigued by that.
That's a great question to put.
Could you repeat?
What do you mean by category-based programming?
Category-based programming. Oh, okay. That is a longer discussion, because if you are thinking about, for example, objects, that is a really great question, but we haven't released the documentation yet. So if you are thinking about different approaches to types, let's start with object-oriented programming, classical object-oriented programming. You have inheritance and all the evilness of it. And in fact, when we are thinking right now about type systems, there's really not much of programming languages that think about types as like about categories of things. So for example, in Luna, all the types are categories in the mathematical sense. So for example, you've got 5, and the type of 5 is also 5. And the type of 5 is also 5, and so on. But also the type of 5 is a positive number. And the type of positive number is an integer. The type of integer is also a double, and the type of double is a number. In fact, if we are thinking about types right now, we are thinking about categories. So if, for example, 5 is in the subset of a number, then 5 is a number. And this is the beginning of such approach. So we treat all the values as some subset of other subsets. And if you are thinking about type system designed this way, based on this approach from the top to bottom, then you are going in the direction of category-oriented programming. In fact,
how is it different from subtyping?
So the difference is that if you've got subtyping, you cannot empower. Okay, there is a lot of difference. So if you've got subtyping, you cannot guarantee that you can inference the types. That's the first thing. The second one is that subtyping doesn't mean that everything is just checked this way. So that, for example, who knows existential types in Haskell? Okay. Oh, great. That's pretty awesome. So in fact, in Luna, we've got some built-in existential types, but also with some kind of inference and with better handling of them. So for example, you can create a list of integers, strings, and vectors. And in fact, this is a group of things that you can put into functions that need some objects from a broader category. Okay? So, for example, this allows you to create some really awesome existential-like types, but much easier, and it is just built into the base system of Luna. And in fact, I think we need to explain this really, really well and really, really slowly in the documentation that we haven't yet released.
We definitely do.
Yeah, but what I have said right now does make a little bit sense for you?
No.
That's not good.
That's fine. Let's talk about it later, please.
I would suggest try to implement it in Haskell as an extension to GHC and point out very well where it fails, hear advice from people, and when there is agreement that it fails for some fundamental reason, because this is a different family of languages, Luna, than Haskell, and just it's incompatible with choices in Haskell, and you need another branch of the programming language.
Yeah, but
then that would be very convincing.
Yeah, of course, but I don't think that we have such great amount of time right now to put our effort to implement that in GHC. This is because we are a company. We are funded by venture capital right now, and we want to really bring functional programming to the broader audience, to the companies that are not yet using it, to IoT building developers and so on.
But you get a lot of peer review of your design.
I completely understand that. I completely understand that. But in fact, extending Haskell right now and making Luna needs more Wojciechs and more Marcins and more.
Yeah.
We are in 4 people.
10 times more or something.
Exactly.
Yeah. Definitely.
Are there any other questions to Marcin or me at this level? So we can just go into some compiler details, if you like to. But in fact, I will try to keep it simple. No, really. Let's make something like that. Yeah, really simple. Okay. So, in fact, I really loved what Oli was talking about in Haskell, because if you are designing systems in Haskell, you really spend a lot of time thinking about nice design, and that is cool. Because thinking about nice design is much more productive than just coding. And if you are thinking about a compiler, it is really simple. So there is Luna compiler, and there are other languages, and this is the graph of our solution. So it's pretty simple. Yeah. Okay, do you have any questions? That's great. So, in fact, I will be making here some assumptions, and then I will tell you that they were a little bit false, but it is much easier to go this way than going the full path at the beginning. So let's assume that Luna is just some Luna stuff and GHC compiler. Okay? So let's say that Luna is some Luna stuff and the Haskell compiler. And in fact, this is exactly very similar to the approach that GHC compiler is some GHC stuff and C compiler. Because, yeah, another funny diagram. So in fact, if you've got some external C code in GHC, GHC has to compile it, has to understand it and link it. So basically, it is something like that. But go back to the basic design. So let's dig into the GHC compiler. Out of curiosity, how many of you could, for example, from the memory, tell how GHC compiler works? Really roughly.
How broadly? I guess that's the question.
Roughly,
It's complex.
okay.
Sticks into the
Yeah, exactly. That was what I was talking about. So, yeah, basically, okay, this is a little bit more.
Yeah, that's what I meant.
Yeah, exactly. So we've got Haskell code. Haskell code is converted into some abstract syntax tree. I love Polish words from abstract syntax tree because only that would be really interesting for you because abstract syntax tree in Polish is drzewo rozbioru gramatyki formalnej języka. This is great. do you want to try to finish?
Let me have a couple of drinks later.
Okay, we'll try that. So Haskell code is converted into AST, so this drzewo rozbioru gramatyki formalnej. And this AST in Haskell has a lot of, let's say, garbage. So this is not pure AST. It has a lot of things like the line number, the file name, and so on and so on. And this is done because GHC wants to maintain in this way how we throw errors. And there are two ways. We can on the beginning desaturate, but GHC goes the other way. And I think this is a perfect way for making compilers. And AST is communicating with type checker. So what type checker does in Haskell, it just checks the types. Yeah.
How do you say it in Polish?
Sprawdza typy. That is just simple. But I don't know how to tell in Polish type checker, to be honest with you. How do you name it? Sprawdzacz typów? Maybe yeah. So AST communicates with the type checker, and in fact, type checker tells AST about what it infers. So okay, you are the number and you are the string and such funny things. And in fact, the type checking process also checks if all the type classes that all you had thought about it match the definitions and match the data that we have passed there. And in fact, after everything is okay, if there is some error, we throw the error and go back to AST and see what line the error was. And if everything is okay, then the type checker passes and we generate the Haskell core. How many of you have heard about Haskell core? Wow, that's pretty awesome. So, okay. To the rest of you, Haskell core is a really small language that every Haskell program compiles to. It is statically type checked. It doesn't have any type inference involved there, and it is really it is done in such a way to provide really straightforward optimizations for the functional world. You can think about the Haskell core like about LLVM for the functional world. LLVM is the set of optimizations for by the shitty company. What is it? So yeah. So then Haskell core can be either translated to C code, but let's leave this way. It is. I think we will switch to GHC will switch to the upper way. So then we generate some LLVM IR. So this LLVM intermediate code from Haskell code. LLVM makes some optimizations out of it, then we generate object files, and we generate from them bytecodes, and we've got executable file. It's pretty cool, isn't it? Yeah. Okay, are there any questions to this graph? Because we will be extending it in the moment. Cool. So, in fact, if we are thinking about, for example, foreign C in Haskell, it looks like this. So foreign C is, let's say, somehow connected to the LLVM. So if we, for example, have some foreign C code, we just compile it to the LLVM and connect it to the one generated by Haskell. And if we are thinking about, for example, JavaScript, there is GHC.js, this Haskell backend that allows us to generate JavaScript code. For example, as Marcin mentioned, our solution is completely written in Haskell, including the web-based graphical interface. We have created a library that automatically generates WebGL code and WebGL shaders to create our interface. So I can show you a live demo in a moment. But let's go with this topic. And the same way we connect, for example, here foreign JavaScript. So if, for example, we want to connect to some libraries in JavaScript within Haskell and using the GHC.js compiler, so the GHC JavaScript compiler, we are going slightly this way. So in fact, we are treating the GHC compiler exactly the same way. So for us, the foreign Haskell code goes from the left side. Okay? Does it make sense for you? Okay. And now about the Luna stuff. So, in fact, on the beginning we've got a textual and visual representation that is isomorphic to ASG. ASG is abstract syntax graph, not tree. So, this is basically the same. And we are also working, and we plan to work a little bit harder in the future on other representations. For example, the natural language representation. So we really want Luna to be multi-source language. So you can just write in pure English, I want to draw 5 arrows that are red and have 2 balls that are blue and so on. And we want to convert that in the future to textual and visual representation, but that are just future plans. Right now we've got the textual and visual representation here. And our abstract syntax graph is like abstract syntax tree, but in fact our type checker works on graphs. And our language also works on graph processing. Our compiler works on graph processing. And we've got here some optimizations. So on the beginning, Luna is optimized and communicates with our type checker. So basically our type checker works like a type checker, so it checks types. And we then are able to optimize the ASG further. And then we connect to some interpreter. We've got both compiler as well as interpreter in Luna. And in fact, if you're thinking about the diagram that you see right now, there is no need for the GHC at all. That is lower. In fact, I can, for example, run Luna right now only with the upper part. So GHC is optional if we are thinking about for Haskell code, but not only, because we are treating Haskell like C, like our base platform. So in fact, every Haskell and C code is native for us. And for making that, we are generating some core ASG, like core Haskell from our ASG. So in fact, if we are thinking about the whole process, on the beginning we've got the textual representation, we parse it to the ASG, we make some optimizations, we type check it, and we create, after successful type checking, we create the core ASG that is just type checked a minimal subset of our ASG. Okay? Great. And then there is the arrow. So our interpreter, the dashed arrows are arrows that we are yet working on. So they are either implemented or are they slightly implemented or are not yet implemented. So we are working on understanding the object files from the Haskell. So if you've got any libraries written in Haskell or any code written in Haskell, you can just put it into our interpreter so it understands it. And in fact, we are working on finishing this task. There is also another connection to the ASG, and this one we will be working in the upcoming months. So from our core ASG, we want also, and we've got some prototype here, to generate the Haskell code. So in fact, if you've got the textual or visual Luna, we are going over our optimization, our type checking, and then we are going the Haskell way. So we generate the Haskell core and going over LVM or to the bytecode or to the JavaScript. So this is how our approach uses the Haskell compiler. Okay? Does it make sense for you right now?
Sorry, I'm a bit lost. So do you actually compile it through Tor or compile somehow? No, you interpret directly.
So both. In fact, both. So you can either use interpreter or you can go to the core. In fact, the interpreter is the version that is completely working right now. We are still working on the core version, and our solution is is really funny because if you are thinking about these nodes and you connect these nodes, the layer that you are working on is interpreted, but every single node, like Martin told, is created out of another graph. And this graph is compiled, and it is object code. So the layer that you're working on is interpreted, but everything deeper is just compiled. And this way we remain really big performance here. Okay? And yeah. And now about other languages. Because Haskell and C and Luna are the native languages for our system. But we are also providing support for other languages like JavaScript, Python, R, and so on. So we are working on these things right now. And it looks like this. We've got something that we call foreign services. And foreign services are, for example, Python interpreter or JavaScript node that we start as a service, as another process. And we want to, for example, transfer some data from Luna into JavaScript, which is automatically serialize the data and automatically generate some data structures in JavaScript to deserialize the data there. So in fact, connecting to JavaScript or Python is just copy-pasting the languages into our system. If you, for example, create a data structure in Luna, you can just access this structure within Python or JavaScript. And in fact, what I have told you about this approach is a little bit false, because it looks like this. So, in fact, so the difference is that we've got nothing like core ASG. In the second picture, there is no core ASG. Everything is on ASG that is interconnected. Yeah.
So how are you dealing with those little things that are very annoying? For instance, the different handling of numbers in Python and JavaScript.
Oh, that is a long story. I've got a really interesting question to you. If we are talking about JavaScript, can we talk a little bit about JavaScript?
Probably not. That's not true.
I would love to. Okay, but maybe in a moment. Because Marcin, I think you have showed me an example in JavaScript and asked me what is the result. And yeah, that was perfect. So okay, in fact, our ASG is created in such a way that we control from the type level of Haskell structure if this is ASG, or this is core ASG, or this is somehow limited ASG. In fact, we've got about 16 versions of ASG. And for example, when we start to compile Luna, we start with so-called dynamic ASG. So for example, we start with assumption that not every type is known at compile time, and it could behave somehow like Python. But if our type checker goes this way and see that, okay, all the types can be inferred during the compilation time, then we just change the type of the ASG to the static ASG. And we can change the type to the core ASG after the whole process of compilation. So in fact, if you are thinking about Luna, Luna allows you to program like in Python with dynamic typing, but in fact we don't support it right now. So our type checker just throw error if it doesn't know all the types at the compile time. But our design allows us to do something really interesting. You can, on the type level, create as many versions of ASG as we want to define the details of the language as much as we can.
Możesz to zdanie powtórzyć po polsku, bo nie zrozumiałam.
Jasne. Może tak będzie łatwiej. Oli, can I say that again in Polish?
Yeah.
Okay, great.
Because I didn't understand it.
Maybe I'll get the Polish version.
Okej. W każdym razie my mamy takie coś śmiesznego tutaj napisanego, że nasze ASG, czyli ten graf języka, ma w systemie typów Haskella zakodowany swój wygląd. Nie, to ja nie będę tam patrzył. W każdym razie, jak zaczynamy kompilować Lunę, to my zakładamy, że możemy nie znać wszystkich typów podczas kompilacji. I jeżeli to założenie utrzymamy jakby do końca, to Luna może działać tak jak Python. Obecnie nie mamy dlatego supportu, nasz type checker wyrzuci wtedy błąd, natomiast jeżeli udowodnimy, że wszystkie typy są faktycznie statyczne w czasie kompilacji, to zamieniamy typ z Dynamic ASG na Static ASG i w tym momencie sam system typów Haskella nie pozwala nam stworzyć takiego grafu, który nie byłby poprawny i nie miałby statycznych typów. Co jest ciekawe, jeżeli my na przykład nasz type checker dalej rozpozna, w jaki sposób ta ASG działa, to my możemy dojść do Core ASG i jeżeli zmienimy typ ASG na Core ASG, po prostu napiszemy sobie w systemie typów Haskella, że to nie jest Dynamic ASG, tylko to jest Core ASG, to w tym momencie ten nasz graf nie będzie mógł zawierać niedozwolonych rzeczy, które nie przewidzieliśmy w Corze. Ja zaraz o tym trochę powiem, bo pomyślałem właśnie, że jak Oli mówi o takich fajnych rzeczach, jak bezpieczeństwo typów bazujące na typach Haskella, to pokażemy wam, jak to zaimplementowaliśmy w środku. Czy to jest mniej więcej zrozumiałe teraz? Super. Okay, we are back. Okay, so in fact, one more word about how NodeLab works and how our whole ecosystem works. So we've got here two API points. The first one is the interpreter, and the second one is API for transforming ASG. So in fact, if you are working on NodeLab, the users are transforming ESGs. They are making diffs of ESGs and they are sending them to us. Yeah.
Just show you
Excuse me?
10 minutes.
Yeah, I will end in 10 minutes. Okay, and in fact these two APIs are connected to our bus system. So bus system is some hub for communication. To the bus system we are connecting NodeLab web graphical interface, so many users can connect to the bus system. And the bus system is some hub that we connect, for example, project manager or Android manager to it, and it sends messages between the different services. So in fact this is the architecture of NodeLab in general. And in fact, foreign services, when you are thinking about this approach, are also connected to the bus. But it was easier to understand this image on the bottom, on the beginning, than this one. And okay, let's say about some funny things. So here is some snippet of our code. This is Luna syntax term expression symbol, and this. I can stand on it. Yeah. Okay, good. So these are our data types that define what type of nodes we can have. For example, the lam is lambda, and the lambda needs some data filled into. But in fact, we are using the Haskell type system really heavy, and we are defining empty data types to just indicate what is the type of the structure, and we are filling this a little bit later. So for example, if we are looking at Luna syntax term expression atom, we've got here a data family atom, and we can see something like that data instance atom for lambda has a list of arguments and a parameter that is the result of lambda. And this is very interesting because I don't want to dig into the details. I want just to show you that, for example, that this is really extensible way of expressing a graph system. In fact, what you see here is just definition of a graph representation that can be fully extensible, and we can just, using the type system, say what this graph has inside. And going back to the slide, is it understand that, for example, atom carry is a data type that has two arguments? Okay? Great. So the last thing that I would show you is this is format. Yeah, this is the term format. This is the Luna syntax term format file. And what it says in the type level says that, for example, if we are thinking about literal, so if we've got in our graph, abstract syntax graph, some node that is called literal, the literal can be either star or string or integer or rational. And this is coded on the type level. If I put here a comma and write something else, our graph representation would allow me to put something like that into the graph representation if it is literal. And again, when we are, for example, defining the value, if we've got something that we call the value in the graph representation, it is either cons lam or any element from the literal list. Again, func, phrase, and draft are the definitions of the graph system. For example, the draft has something that is called missing. And missing is used by NodeLab is if somebody is defining the system but hasn't collected some parts of it yet. Okay? Okay, so that was some interesting data inside the implementation of the compiler. I would love to dig later about it when we.
So these are type level lists. Is that what you mean?
In fact, yeah, that are just type level lists. But when we define these lists, they define how the graph behaves. So, for example, if I type my graph that it is the ASG value, we would allow them only to have cons lam, star, string, integer, and rational elements inside. And what is more interesting, we are not only talking what values we can have in this graph, but also how they are connected. So, for example, if we are talking about dynamic graphs, then when we are evaluating function, the name of the function can be a node, but if that are static graphs, it has to be a string. So, using the type level, we design the graph and dependencies of the nodes. So we are sure that, for example, static graphs are resolved by names at the compile time. Okay?
Can I add something to that?
Yeah.
So there's also the pretty cool way of ensuring progress of our compiler on the type level, because, for example, you can you cannot have an element of a lower in the hierarchy connected to something higher in the hierarchy. So basically, a func cannot have inputs that are drafts.
Yeah.
So that basically allows us to ensure that our compiler is making progress, or our type checker is making progress. Because if it moves graph from the draft level to the func level, that means we have progress and we have basically narrowed the set of possible elements.
Yeah. So if you narrow some element, you have to assure that all the inputs are also narrowed. So this way we are compiling the graph to the much closer representation of the core AST. Okay. And in fact, here is some screenshot, or is it not? Okay. Here is some interesting screenshot. It is completely unreadable in the visual representation because it is really low level implementation of something. But just going yesterday to Warsaw. We have seen that on the screen of our friend, and he was just defining the WebGL library in Luna. And what he does here is he is just creating some circles, filling them with color, making some singletons into shader, compiling these shaders into the WebGL shader, and defining some sinusoid function and applying this to the visualization. But that doesn't matter. In fact, when we create some better libraries in Luna, that would be 2 or 3 nodes. This is just a placeholder for Adams to work on it. But what is interesting, we just cross the border with Luna that we can define WebGL shaders with our nodes, and we can just display these shaders within our graphical interface. So in fact, we are moving into this direction. So that was some insight into our compiler, and I have 1 minute left. So let's do some questions. Yep.
Seen from the file graph, you do some optimizations before type checking. So how do we make sure that
the optimizer doesn't modify the ASG so heavily that type errors become unrelated to the original source?
Yeah, that is a great question, and in fact we are not making any optimizations pure type checking. As you can see, we are making optimizations on the ASG with collaboration with type checker. So if we are type checking something and we know some more properties about it, then we can optimize it. Okay? So in fact, without type checking, we are making also some optimizations, but if we know the types pure, the pure type checking, then we know that they are true. So after pure running the type checker. Okay? Are there any other questions regarding? And who wants to write compilers? Great. Let's talk about it later because we are looking for people. That's really cool. Okay. Are there any other? Okay, great.
So you compare to Haskell core. So do you have a Haskell FFI that
yep.
is?
If we are compiling to Haskell core, then we can gain everything from Haskell, including the threading model, the garbage collector, and so on.
Is it more expressible than every FFI out there? So do you translate some subset of Haskell types to Luna types? And
yep. Yeah, we have that is very interesting thing because okay, I will tell you something. When we first designed Luna, and we made prototype of it in our previous startup that is working great and it is alive, but it is managed by another people right now. By the way, my ex-boss from the visual effects studio that I was working on So we have created the first type checker of Luna, just prototype of it, using template Haskell on top of Haskell. That was pretty awesome thing, but yeah, I forgot your question.
I just
I'm sorry.
Whether I can use some Haskell libraries from Luna.
Yeah. So we are treating Haskell and C as native code for our platform, and in fact, not every Haskell code is just straightforward usable in Luna, but we analyze, we somehow analyze the code and making automatic bindings that are free and that are just new types and they are just freed at compile time. So there is no performance overhead over using Haskell or C in Luna.
It's cool.
Thank you.
That makes it actually usable because else you would have to rewrite code.
Yeah, exactly. It is no point for us to make every library from the ground up. So we can just use every Haskell library without performance overhead, and the same goes with C.